The 140% factor is used in feeder calculations for generator field control because the field excitation current may increase by up to 40% during transient conditions such as starting or load changes. This increase in current is higher than the normal operating value, and therefore a larger conductor size is required to accommodate the higher current flow. The continuous rated motor column in Table 430.22e is used to size feeders for continuous duty motors, such as those used in pumps, fans, and air conditioners. Elevator operation, on the other hand, is considered intermittent duty, as it involves short periods of high current draw followed by periods of rest. Therefore, the first three columns of the table, which are for intermittent duty motors, should be used for sizing feeders for elevator operation. Let's delve deeper into why the 140% factor is essential for generator field control. During events like a generator starting up or experiencing sudden load fluctuations, the magnetic field within the generator needs to adjust rapidly. This adjustment demands a surge in the field excitation current. The standard operating current isn't sufficient to meet this transient demand, hence the need for a higher current carrying capacity in the feeder conductors. This 40% increase accounts for this potential surge, preventing voltage drops or conductor overheating that could compromise the generator's performance or even cause damage. Now, let's clarify the purpose of the continuous rated motor column in Table 430.22e of the National Electrical Code, or NEC. This column is specifically designed for sizing feeders that supply motors intended for continuous operation. These are motors that run for extended periods without significant breaks, such as those found in pumps, fans, and air conditioning systems. Because these motors operate continuously, the feeder conductors must be sized to handle the sustained current draw without exceeding their ampacity ratings. However, not all motors operate in this manner. Elevators, for instance, represent an intermittent duty application. They cycle through periods of high current draw during acceleration and deceleration, interspersed with periods of rest when the elevator is stationary. This intermittent nature significantly impacts the feeder sizing requirement. The NEC recognizes this difference and provides separate guidelines for intermittent duty motors. The first three columns of Table 430.22e are dedicated to these types of applications. These columns allow for a lower conductor ampacity compared to the continuous rated motor column because the motor is not drawing its full rated current continuously. Using the appropriate columns for intermittent duty motors like elevators can result in significant cost savings by allowing the use of smaller conductors. Remember that selecting the correct feeder size is crucial for safety and reliability. Undersized conductors can overheat, leading to insulation breakdown and potentially causing fires. Oversized conductors, while safe, represent a necessary expense. Adhering to the NEC guidelines and understanding the specific operating characteristics of the motor being supplied is paramount. In summary, the 140% factor is applied in generator field control feeder calculations to accommodate transient current increases during starting and load changes. The continuous rated motor column in NEC Table 430.22e is intended for motors operating continuously, while the first three columns of the table should be used for intermittent duty motors like those found in elevators. Properly sizing feeders ensures safe and efficient operation of electrical equipment. Consider a scenario where a generator is powering a critical facility. During a sudden power outage, the generator kicks in to provide backup power. As the generator starts up, the field excitation current momentarily surges to build the magnetic field. If the feeder conductors supplying the field control are not sized appropriately using the 140% factor, the voltage could drop significantly, potentially causing the generator to fail to reach its rated output. This could lead to a disruption of critical services within the facility. Conversely, if the feeder conductors are correctly sized, they can handle the transient current surge without significant voltage drop, ensuring that the generator starts smoothly and delivers the required power. This example highlights the importance of understanding and applying the 140% factor in generator field control feeder calculations. Let's consider another scenario involving an elevator in a high-rise building. The elevator motor operates intermittently, accelerating and decelerating as it transports passengers between floors. If the elevator feeder were sized using the continuous rated motor column in Table 430.22e, the conductors would be significantly larger and more expensive than necessary. This is because the elevator motor does not draw its full rated current continuously. By using the appropriate columns for intermittent duty motors, the feeder conductors can be sized more accurately to match the actual current demand of the elevator. This not only reduces costs but also ensures that the electrical system operates efficiently. The NEC provides detailed guidelines for sizing feeders for various types of motors and applications. It is crucial to consult the NEC and understand its requirements to ensure safe and code-compliant installations. Ignoring the NEC guidelines can lead to hazardous situations and costly rework. Always consult with a qualified electrical engineer or electrician when designing and installing electrical systems. They have the expertise to properly size feeders and ensure that all applicable codes and standards are met. In addition to the 140% factor and Table 430.22e, there are other factors to consider when sizing feeders for motors. These include voltage drop, ambient temperature, and the number of conductors in a raceway. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause motors to operate inefficiently or even fail to start. The NEC recommends limiting voltage drop to a maximum of 3% for feeders and 5% for branch circuits. Ambient temperature is the temperature of the surrounding air. Higher ambient temperatures can reduce the ampacity of conductors. The NEC provides correction factors for adjusting conductor ampacity based on ambient temperature. The number of conductors in a raceway can also affect conductor ampacity. When multiple conductors are installed in the same raceway, they can generate heat, which reduces their ampacity. The NEC provides adjustment factors for directing conductor ampacity based on the number of conductors in a raceway. By considering all of these factors, you can ensure that your feeders are properly sized and that your electrical systems operate safely and efficiently. It is important to stay up to date with the latest version of the NEC, as the code is revised every 3 years. Changes to the code can affect feeder sizing requirements. Attending electrical training courses and seminars can help you stay informed about the latest changes to the NEC and best practices for electrical installations. Remember that electrical work can be dangerous. Always de-energize circuits before working on them and follow all safety precautions. If you are not qualified to perform electrical work, hire a licensed electrician. They have the training and experience to perform the work safely and correctly. In conclusion, understanding the 140% factor for generator field control and the proper use of NEC Table 430.22e is essential for safe and efficient electrical installations. By following the NEC guidelines and considering all relevant factors, you can ensure that your feeders are properly sized and that your electrical systems operate reliably. Always consult with a qualified electrical professional if you have any questions or concerns about electrical work. They can provide expert advice and ensure that your installations are code compliant. Remember safety first. Now let's discuss some of the common misconceptions about feeder sizing. One common misconception is that you can simply use the motor's nameplate current to size the feeder conductors. While the nameplate current provides a starting point, it does not account for factors such as starting current, intermittent duty, and ambient temperature. Another misconception is that you can always use the smallest possible conductor size. While using smaller conductors can save money, it is important to ensure that the conductors are adequately sized to handle the current demand without exceeding their ampacity ratings. Undersized conductors can overheat and create a fire hazard. A third misconception is that you can ignore the NEC guidelines if you are working on a small project. The NEC applies to all electrical installations regardless of size. Even small projects must be code compliant to ensure safety. A fourth misconception is that you can rely solely on online calculators to size feeders. While online calculators can be helpful, they should not be used as a substitute for professional judgment. It is important to understand the underlying principles of feeder sizing and to consider all relevant factors before making a decision. A fifth misconception is that you can always use aluminum conductors instead of copper conductors to save money. While aluminum conductors are less expensive than copper conductors, they have a lower ampacity and require larger sizes to carry the same amount of current. In some cases, the cost savings may not be significant. It is important to carefully evaluate the pros and cons of using aluminum conductors before making a decision. A sixth misconception is that you can always use the same size conductor for the neutral conductor as you use for the phase conductors. In some cases, the neutral conductor may need to be larger than the phase conductors to handle harmonic currents. Harmonic currents are non-sinusoidal currents that can be generated by electronic devices. If you are unsure about the proper size for the neutral conductor, consult with a qualified electrical professional. A seventh misconception is that you can ignore the voltage drop if you are working on a short run of conductors. Even on short runs, voltage drop can be significant, especially for high current applications. It is important to calculate the voltage drop and ensure that it is within acceptable limits. An eighth misconception is that you can always use the same type of insulation for all conductors. Different types of insulation have different temperature ratings and are suitable for different applications. It is important to select the appropriate type of insulation for the specific application. A ninth misconception is that you can always use the same type of overcurrent protection for all circuits. Different types of overcurrent protection are designed to protect against different types of faults. It is important to select the appropriate type of overcurrent protection for the specific circuit. A tenth misconception is that you can ignore the grounding requirements if you are working on a low voltage circuit. Grounding is essential for safety, even on low voltage circuits. It provides a path for fault current to flow back to the source, which can trip the overcurrent protection and prevent electric shock. By avoiding these common misconceptions and following the NEC guidelines, you can ensure that your electrical installations are safe and code compliant. Always consult with a qualified electrical professional if you have any questions or concerns about electrical work. They can provide expert advice and ensure that your installations are safe and reliable. In addition to the technical aspects of feeder sizing, it is also important to consider the economic aspects. Properly sized feeders can not only ensure safety and reliability, but also reduce energy costs. Oversized feeders can result in increased material costs and higher installation costs. It can also contribute to increased energy losses due to the larger conductor size. Undersized feeders can result in voltage drop and reduce motor efficiency, which can also increase energy costs. By optimizing feeder size, you can minimize both initial costs and operating costs. Another important consideration is the future expansion of the electrical system. If you anticipate that the electrical load will increase in the future, you should consider sizing the feeders accordingly. This can save you the cost of having to upgrade the feeders later. However, it is important to avoid oversizing the feeders too much, as this can result in unnecessary costs. A good approach is to estimate the future load and size the feeders to handle that load with a reasonable margin of safety. It is also important to consider the availability of materials and equipment. In some cases, certain sizes of conductors or overcurrent protection devices may be difficult to obtain. If this is the case, you may need to adjust the feeder size accordingly. However, it is important to ensure that the adjusted feeder size still meets the NEC requirements. Finally, it is important to document all of your feeder sizing calculations. This documentation can be helpful for future reference and can also be required by some building codes. The documentation should include the motor nameplate information, the calculated current demand, the conductor size, the overcurrent protection size, and any other relevant information. By considering all of these factors, you can make informed decisions about feeder sizing and ensure that your electrical systems are safe, reliable, and cost-effective. Remember to always consult with a qualified electrical professional if you have any questions or concerns about electrical work. They can provide expert advice and ensure that your installations are code compliant. Safety is always the top priority.